Good afternoon, everyone, and thank you for joining this afternoon's seminar. So this afternoon, the seminar will be given by Dr. Luis Perenon from UWC, and he'll be talking about agnostic cosmology and multitasking, the growth of cosmological structures. So take it away.
Thank you very much. Thank you very much for having me. It's really a pleasure to give you this talk today. I really wish I would be with you in person. I've actually been wanting to come to Durban for quite a while, but I guess the current situation doesn't allow that. So what I'm going to talk about today is some work we've recently put on archive with my collaborators that you see here. This work doesn't warrant talking for 40 minutes, maybe just half. So what I decided I'd do is, well, obviously start a bit with context, but I wanted to attract the attention and maybe debate a bit what we understand or what we think about all these questions of model independent tests, agnostic approaches, and how machine learning is starting to give us new insights and is going to be, I think, give us some very powerful tools to use in the future with all those surveys that we are craving for. And only then will I discuss the work that we did. I just want to say this agnostic section that I'm going to talk about is very new to me. And so there's probably a tremendous amount of work that has been done in there, which I probably don't know about. So this is kind of my general view that, an humble view that how I see it for now. And I didn't cite references in this section very much, simply because there's too many. So if anyone wants to ask details, etc., and I'm very happy to answer, but I didn't feel like I knew enough the literature about that, so I didn't put anything as references. But yeah, anyways, so let's start the good old standard model slide. So I just want to recall that one of our founding principle, the cosmological principle, is that the universe at large enough scales is inhomogeneous and homogeneous and isotropic, which means that you can describe that universe with this Robertson-Walker metric. If you couple this metric to Einstein's equations, then you obtain those extremely powerful equations that describe how the background evolution evolves. So yeah, the background describes the background evolution of the universe, and technically this characteristic scale of the universe, the scale factor, is just you model it as being as evolving and evolving with respect to the different energy content in the universe. And this energy content, we describe it generally in a fluid approach. So every different type of energy content has a different equation of state parameters. Anyways, and this is incorporated in the standard model, and basically from the gravitational point of view, lambda CDM is GR, where you add this cosmological constant. And within that, we understand that actually about 70% of the energy content of the universe is what leads to having cosmic expansion. So we have a great model that has been tested a lot, and a lot of observations give a nice consensus, but it's not perfect yet. And you have several problems that you could raise about our standard model. I think the most well-known, or the most well-known from the theoretical point of view, is that if you want to attach the evolution, this cosmic expansion to be, so the cosmological constant to be attributed to vacuum energy, well, use the energy densities between observations and theoretical prediction differ by an enormous amount of orders of magnitude. So that's a kind of a big problem. Another problem that is cited sometimes, although I have harder times to accept, is just to say that how come cosmic acceleration, or the dominance of dark energies, has actually happened around today. I think there's another thing we've heard about more recently is the fact that, well, we do see very large scale structures, and that actually could be leading to conflicts with our cosmological, the Copernican principle. On the observational side, we have been hearing a lot about observational tension, especially with the H01, which is really now a hot topic. So the point is that if you measure H0 from local measurements or you extrapolate it from CMB physics, you end up with a huge tension. I don't even quote a number because I don't know what's the last tension, the number, but it's probably more than 5 sigmas. So concerning tension. Another one in the more that concerns the perturbed sector of the universe is the fact that kids, weak lensing and Planck don't want the same amount of the amplitude of matter perturbations, I think from weak lensing is lower than what you get from Planck. So that translates into this tension on sigma H0. Sigma H0 is the amplitude of the power spectrum, the normalization of the power spectrum, if you want. We'll talk about this later. So all that to say that with these, that sends theoreticians to go work very hard and end up giving us a huge range of possible alternatives to our standard model. So that gives us very rich theories and understanding, etc. But on the phenomenological point of view, it is kind of a nightmare, because eventually what you want to is constrain all those possibilities and study which one is the best with respect to another. So you can imagine that practically in this approach, you'll have to code something that is like CAMB for each of those scenarios, because at each time you'll have kind of different equations of motion. So that is just an impossible task in general. But I mean, obviously with a lot of work, we could go there, but the amount of theories that come out with respect to the amount of stringent constraints on these theories, I think the balance is not quite there. So this motivates why, although the previous approaches are very important to understand the fundamentals of the universe, there's also this approach that this big word that we hear a lot, which is model independence test. But I'm wondering that might be quite an ambitious term, because can we really be model independent? Are we not chasing an illusion in a certain sense? And maybe more practical than that, do we have a common definition of what model independence is? And I believe we don't, because different people have different definitions. What I would say is that basically when you use observations and you want to constrain theories, you can go theoretical. So you really have two models. And given observations, you can do your Bayesian statistics, end up computing a Bayes ratio between the two models, and you'll say all those observations favor this model over the other one. So here I write all probe combination, because ideally what you want is you test your models with all the cosmological observations that you have, and even astrophysical. And then you can be quite sure at a given significance, as always, that one model is better than the other. But still, this is a relative comparison. So that means you will have to, constrain all the models. So that is what I was referring to as a lot of work. There are parametrized approach. So these I will go through a bit in details after. But you have parametrized approaches where you can parametrize a large class of models, and therefore when your coding will be less, because you will be able to encode within the same framework different theories. Another parameterized approach, which is more phenomenological, is that you'll invent phenomenological descriptions of physical effects. So we'll see that, but for example, the evolution of the dark energy equation of state can make it effective. And so this, you will still be able to compare two choices and have a Bayes ratio. But in that context, you probably won't be able to use all the probes. For example, if I'm working really on W, well, in principle, there's certain things, certain observations that aren't sensitive or at least enough to this evolution. So your comparison will not be able to take into account enough observations. And now we're getting into more the heart of the talk, and a lot of what has been going on is data-driven reconstructions. So now this is more of an absolute claim, because you're saying, I'm going to take a sort of model-independent approach. I'm reconstructing data. So I forget about any gravitational model. I reconstruct the data, and I say the data gives this given function to be this with those errors. And I see, for example, that the prediction of a given model doesn't match that. And you're going to say, well, the data in principle excludes the model. But so this is important information, but now I wrote fewer probes, because basically what you're doing, you're just using one probe to make a statement. This probe doesn't favor that model. But for a model to be true, you want to, again, to go back to the previous and it to fit all the probes to have a final answer. So it is very technical, and I think all the approaches are very valuable, but I just wanted to point out that, yes, it is technical. And do we know exactly how far can we say in terms of statistical significance, once we have a data-driven reconstruction that excludes a model, does that really exclude the model, for example, etc. And so this motivates why machine learning is really starting a new chapter of cosmology, is because I believe that those are the techniques that will really bring us to doing truly model independent tests, or at least what I want to call, or what has been recent. I mean, you hear more and more, is more model agnosticism, in the sense that you're going to do a study which has a model, because probably there's statistics behind. So, but it's agnostic to your gravitational theory. So you're model agnostic in the sense I'm not taking into account any gravitational theory, and I'm choosing to fit my data, etc., with something different, maybe a more statistical machine learning approaches. So what I'm going to talk about now is just go, sorry, I keep shifting. Yeah, just maybe go through the most model independent approach within the model independent approaches. So I was telling you about those parameterize, where you parameterize your theories, like large classes. You probably have heard of the PPN, parameterized post-Newtonian formalism. This is a weak field expansion, is valid in the weak field gravity regime. It's an expansion around the Minkowski metric. And this has been very valuable because it's shown, thanks to constraining the parameters of the expansion, how gravity behaves extremely closely to what has been predicted by GR at solar system scales, for example. So that's why you know that any dark energy or modified gravity model needs to recover GR on small scales or on generally high density regions as well. You also have the little brother or the little sister, which is called parameterized post-Friedmanian formalism, which is the same kind of idea. There's an expansion of Einstein's equations, and it is able to just model within the same framework any spin zero addition to GR. I really don't know much about these things, so I'm really like just throwing it, like putting it out, because I think it's important to know about these things, but this is really not my specialty. The last that I'm pointing out, there's probably more, I should have put 3 dots, is the effective field theory of dark energy. And this is something I've worked during my PhD on. So here, technically, it's more of a particle physicist description of dark energy, where basically you adopt this 3+1 decomposition of your space-time. You say that actually it captures any new scalar degree of freedom, but the idea behind is that this new scalar degree of freedom is not added ad hoc. It's just the Gaussian boson of the broken time translations that we have in the universe. So this encapsulates, for example, Horndinsky theories, but it has also been extended to GLPV theories or beyond Horndinsky. And then let's say the most general ones that you can have now that are stable are called degenerate higher order scalar I don't remember the S, and T is probably theories. Scalar tensor, beg your pardon, ST is scalar tensor. So now let's go again, maybe something now, those were like general frameworks, but when you do some constraint, you constrain several classes of model that are incorporated in them. For example, high class, the code high class enables you to constrain any model which is within the Horn-NC class. So you will have Browns-Deakin, some quintessence, or etc. of 3 dots, a lot of models. Let's go now to what I entitled parameterized phenomenology, which means now you're more focused on one effect that you observe, for example. So here I give an example of the background evolution of the universe and say that you want to encode be an effective description of dark energy where, and you know that some models can predict that, but you just want to allow for the dark energy equation of state to be redshift dependent. I typed this to, it should be a here, I beg your pardon, because this is simply a Taylor expansion around A equal A0, I mean A0 today. So it should be a here. This is called the CPL parametrization, Chevalier, Polarski, Linder. And here I'm showing plots from the Planck 2018 paper, where you can, so these act a bit as a null test because lambda CDM will have W0 equals -1 and WA is equals 0. So this is the middle of the cross. And you can see, for example, that from this, you'll say, well, Planck CMB alone actually doesn't recover lambda CDM within the 2 sigma contours. But as soon as you add supernovae, this all shifts to including lambda CDL nicely, lambda CDM. So now just a second example that with the perturbations in the universe. So you might have heard of the mu sigma parametrization, mu eta, G matter, G light, X, Y. There's been a lot of names, but basically what's behind that is that you want to, again, phenomenologically allow that your Poisson equation differs from that of GR. So if mu is equal to 1 here, you have GR. And if it's not, then you have detection of a different model. So yeah, that's it. So that really concerns the dynamics of massive bodies, of gravitating massive bodies. And you also want to be able to do that in principle with how light behaves in the universe. So you have this gravitational slip parameter. So the ratio between your Newtonian potential and your curvature potential. And maybe you know more of sigma, because this is the one that would be constrained by weak lensing experiments. Well, I mean, eta is not directly observable. And you see that this forms a trio, okay? So it turns out that here Planck chose to show mu 0 and eta 0. So those are the values of those numbers today. They parameterize this deviation as being proportional to dark energy. So it is a phenomenological parametrization. So you are within the boundaries of this parametrization. Then you can argue how general it is. But same thing here. You see that, for example, CMB alone, it's a bit hard to see, but CMB alone tends to put it outside the confidence, the 2 sigma region. And as soon, again, as you add things like, especially weak lensing, actually, you get, it goes back into the middle. So one of the last general slides is that now let's just like really see what I personally think is really methods that are model agnostic. So that will allow you to say something about what the data wants without invoking any gravitational theories. So something that I know nothing about, but I'm going to work on that soon, is principal component analysis. Something that I'm working on at the moment and why I'm talking to you about today is Gaussian processes. But I can say that I'm still a bit confused by these things. Another thing that I don't know anything about, but I'm starting to work on as well, is genetic algorithms. So this is a machine learning technique that actually allows you to predict functions directly from data. So not parameters of a function, but the function itself. So it's very mysterious to me, but it's very appealing as well. And I think the cherry on the cake in this model agnosticism, and what's really I think can be the future is what we call likelihood-free inference. And for example, deep learning is taking us there, where I'm only started to see a few looking at a few archive paper where basically from maps on the universe, you end up being able to predict the values of cosmological parameters using neural networks. So it's quite, to me, it's completely crazy and fascinating. Okay, now we're getting more into the core of the talk. So a bit of background, let's say, on Gaussian processes. If you don't know what those are, you can just see them as the compilation of random variables, of the distribution of random variables, where each Gaussian random variables, where at each, for example, redshift, one Gaussian random variable will be defined by its mean and a variance, and generally you have a covariance of all the mu's. So that's how you generally define just how you write it down. So the important thing in here is basically you will model this Gaussian process. So G is the function that you want to reconstruct from your data. So the input that you will give is a kernel. So that is basically the thing that will describe how the points are correlated in your reconstruction. So a simple example, and actually something that is most often used in cosmology and that we've used as well in our paper, is the squared exponential. So you see that this is how it looks, and it is characterized by two hyperparameters, sigma, the signal variance, and psi, the correlation length. So those are your three parameters of your Gaussian process. So in other words, the three parameters of your statistical model that you're using to fit the data. So what generally happens, I mean, as soon as you have this, you can predict your whatever reconstruction, but what you do is that you want to minimize your data, minimize the likelihood that you can derive. And as soon as you have that, you can reconstruct your function using how this expression for the mean and the covariance of your reconstruction. So you choose a kernel, you have the likelihood, you minimize that, you find the best fit of those two hyperparameters. In other words, you say you optimize the hyperparameters, and you derive the mean and the covariance. I'm just going to tell you that there is actually a third input that is quite important, is that you have to give a mean prior. So your idea of how the mean of your reconstructed function is, actually this prior can have zero effect or a lot of effect, especially when you have gaps in your data. So this is something that is kind of important when you want to talk about model agnosticism, model agnostic approaches, because obviously if what dominates is your choice of prior, then if your prior is not agnostic, then you can criticize this your claims in a certain sense. Okay, so just a few words on a bit of literature. So the Gaussian processes have been used a lot in cosmology, especially to reconstruct variables that are related to the cosmic expansion. So H of Z, basically. This is I think I've traced back literature to this paper to be the first one to apply Gaussian processes in cosmology. And what was quite funny is that they were doing forecasts in 2000. I mean, I'm sure it's been always their forecasts, but I know today a lot of the Gaussian processes paper use them for forecasts for all our future surveys. And going back to 2010 was quite funny. We use forecasts to test, etc. So they simulate supernovae data. And from that analytics, you manage to reconstruct the evolution of W of Z. So those are mock data. So here, for example, is a reconstruction around a fiducial that is lambda CDM. And here, those two plots are two fiducials belonging to the quintessence models. Another one, I decided to just show this because I haven't talked about cosmography, but in the parameterized modeling, I could have added cosmography as other parameterization, but this is also a sort of model independent way of constraining the Hubble expansion. Of seeing it is where you do a Taylor expansion of H of Z. And this was a paper which coupled those two ideas. So what they actually do is use, I don't know if you have ever, it's an old compilation of supernovae, Union 2.1. And so they constrain the evolution of the Hubble expansion. So here they call it, here is the inverse, but that's what they, whether they apply the Gaussian process. But then through analytics, they get Q of Z, which is the order 1 parameter of your cosmographic expansion. So yeah, I just wanted to mention this as well. There's a lot more that has been done with Gaussian processes in cosmology. There's a lot that is used in instrumentation. So in how to speed up your process to have data, to derive data, your precision, etc., which I don't know anything about, but there's a lot of literature on that. As I said, there's a lot on actually H of Z and other quantities related to H of Z. There's also something that has been quite popular lately, where you couple strong lensing measurements and supernovae data, where thanks to Gaussian process, you will be able to find the anchor of H of Z. So basically, you want to have a way, a model independent way of finding H0. And my point is that on the perturbation, so reconstruction function that describe the perturbation sector of the universe, the literature is more scarce. There's one paper from a collaborator on reconstructing the linear anisotropic stress. So that would be what I presented before, eta. And a few papers on reconstructing F sigma 8 or F, so the growth rate. I will give details about that in a minute. So now let's get to the second layer of Gaussian process. So there's a way to so far I've been just presenting how to reconstruct one function with one given data set. But when you have multiple data sets so therefore on several functions, and you know they're related, you can adopt this multitask GP approach. So basically the same definitions apply. So the likelihood, the mean, and the covariance, those expressions that I saw before, stay the same. But the idea is that now each function that you're going to reconstruct, you choose a subkernel. So you could say each of them will follow a squared exponential. But the kernel that you're going to use to in your likelihood and in your predictions is going to be this compilation of all the subkernels. So you see that you have for function 1, the, let's say, squared exponential, squared exponential, and whatever you want to choose for F3, let's say, again, squared exponential. Then the cross terms now are actually the convolutions of the basis function of those kernels. So now those terms mean that you're taking into account interdependence of the functions. So you're acknowledging the fact that data set A on function A and data set B on function B, function A and B are not independent. The other plus with this approach is that now, if you have between data set, you know there are correlations, and so you're therefore not treating, say, function A and function B, and you know those two had correlations, but since you're doing a single task, a standard reconstruction on A and B, there's no way of talking to each other, so you forget about the correlations, and in principle, you've missed important information. So by doing that, now what you're putting in your likelihood, your kernel is that, and your covariance function is that. So you have the error on function F on the data set function F1, F2, etc. But here you have the cross covariances. So that's what we use in our approach. And I want to first give a lot, beg your pardon for the repetition, credit to this paper. Because when we were looking for a long time how to reconstruct functions at the same time, and I was spending a lot on mathematical papers from statisticians, which I didn't understand anything about. And one day and it was a bit of a struggle. And one day, looking more into cosmology literature, we ended up finding this paper, which were the first to apply this to my knowledge, the multitask approach to cosmology. And they applied it to the reconstruction of cosmic acceleration. So what it means is that they consider 3 different data sets that all have an underlying information on how h of z evolves. So supernovae, BAO, and cosmic chronometers. So you will have the corresponding function Sn reconstruct E of Z, BAO, RD, H of Z, etc. And look here, the result is how now considering those combinations, so doing the multitask, how the errors diminish a lot. So if you just do cosmic chronometers, you see that is plus or minus 5 for H0 kilometers per second per megaparsecs. Ooh, sorry. But now when it starts adding the 3 at the same time, now the error is tiny. Here R12 is just that here they add the HST, latest HST measurement of H0 as a prior. But yeah, so now to the analysis. So we applied that to growth for structures. So just a reminder, growth for structures is a tracer of how matter perturbation evolves. So this delta M, in lambda CDM, delta M will follow this differential equation, but delta M is not directly observable. For example, something we know that characterizes delta M is what we define as the power spectrum. For example, as I was saying earlier, sigma 8 is a measure of the amplitude of the power spectrum. Here we're interested about its redshift evolution, and generally this is encoded by the linear growth rate here, and typically the growth of structure function that, the characteristic is f sigma 8. And why is that? It is because redshift space distortions give you data on f sigma 8. But I want to point out that recently collaborations have used combinations of, for example, RSD and galaxy-galaxy lensing, or combination of RSD and with the bispectrum as well. So having the power spectrum and the bispectrum to actually break the f sigma 8 digit under a C. And so we have a little sample now of measurements of f sigma 8 and the f and the sigma 8. So with this in mind, why not reconstruct those 3 functions with multitask GP, especially knowing that stage 4 galaxy surveys will give us measurements of those 3 functions. So we did mocks. So our setup is to consider Planck 2018 as a fiducial constraints. As I said, we want to be within the context of nominal stage 4 galaxy surveys, and we want it to be very simple, just to be able to really explore the multitask approach. So we just consider 20 measurements distributed around 0 or 2. So this is to imagine measurements that we'll get, for example, with SKA and EUCLID, etc. We decided that for the same reason that we're just going to model the errors on the data as just being 1% relative error with respect to the fiducial, and a mock is simply drawn by the multivariate Gaussian, which is defined by the fiducial as the mean, and this 1% relative error times the fiducial as your covariance matrix squared. I forgot the squared. I just want to point out that we are releasing the code that we use, and we are looking into making it much more professional in the future with our chapter 2 coming. So yeah, I just want to maybe point out that with we found that multitask GP tend to give you a bit more weird likelihoods where you might have non-global minima. So we found that it wasn't a good idea to use standard gradient ascending or descending minimizers. So we tend to we included the stochastic minimizer from this SciPy package. We've also interfaced Cobaya is Metropolis hasting and polychord nested sampler and EMC in the code. For the same reason that I said before, we found that it was very important to use a nested sampler to sample the hyperparameter space of multitask GPs. And we use this for the plots and the post-processing. Okay, main result here. the joint reconstruction of our mock on F sigma 8, F and sigma 8, you see I've simply subtracted the fiducial so you can see more clearly the differences. You have single task in gray and multitask in red. So remember, single task just means that this gray reconstruction that just takes into account this data set, while the multitask, you're reconstructing those three things at the same time. So you can do several observations. Maybe the most striking one is that at this level of precision, the GP is really sensitive to the spread of data around the fiducial. So it is wiggly. You might also see that the red is more wiggly than the green. The other thing that you should see is that the means aren't the same. So the redshift evolution predicted by single task and multitask is not the same. And lastly, the errors tend to be smaller. So this shading around the mean is a 68% limit. Sorry, and those are smaller in the MTGP case than in the STGP. So, which means that the sharing of information when you do this joint reconstruction has important effects, those that I just cited. We did an MCMC exploration, so this of precisely this data set. Just to, in a few words, here you see now that it's MTGP, you consider those 6 hyperparameters at the same time. So the 2 on F, the 2 on sigma 8, and the 2 on F sigma 8. While your single task, you do 3 independent single tasks. So that's why there's those 3 plots here. So it would be, you wouldn't see anything if I over plotted this here, because from here to here, you might not realize, but the size of the contours here has increased a lot. And another thing that you should see is that the values of the hyperparameters have also increased a lot. And this is all the result of now considering all the data sets together. But you do see that the correlation that you have between the 2 hyperparameters within the same reconstruction remains. So you still have this 45-degree diagonal. But obviously, because you have those new degeneracies by considering jointly all of those parameters, then you have all those new features that you have. And that also explains why the contours enlarge a lot. To go further, we wanted to have more statistics to see what happens. So we just generated a huge amount of mocks. And what we found to see how better is multitask and is that a recurrent thing. So we do see that every time, I mean, over the whole generation, the log likelihood of the MTGP is always bigger than the sum of those 3 MTGP multitask, Gaussian process, STGP, single task, of those 3 single task reconstructions. Another thing that we thought about to compare how better the fit is when you do multitask GPs is a chi-squared. That it's just a hybrid chi-squared where we consider the reconstruction, we discretize the reconstruction, and basically for a given function, we pick 50 redshifts of the reconstruction. So we have the covariance thanks to the GP predictions and the mean, and we compare that with respect to the true underlying model, which in our case we know because it's the fiducial. And you see that for each functions, well, the MTGP does better. And that kind of gives us an important information, because if I go back to here, the gray reconstruction will be the most faithful to data in terms of the redshift evolution, because this doesn't, in a certain sense, doesn't get polluted by the other effects. But the other thing that happens when you do MTGP, as I said, is that those errors reduce. So in the end, we find that the chi-squared is always better with multi-GP, which tells you that really what dominates the goodness of fit or the betterness of fit of MTGP over an STGP is the fact that you decrease the errors. So we were just to come back to the fact that we don't recover the fiducial is maybe a bit, it might be a bit weird that you don't. So we just decided to compute over all our mocks what is the average distribution of all the reconstruction, and you see that now you recover the fiducial within the 1 sigma errors. But it's not flat. So even though you have 10,000 mocks, well, you still don't have something flat. So maybe to have something flat will take an enormous amount of mocks, but at least we're satisfied there's no bias hidden in there. The other thing is that those deviations are actually a good thing. So this plot just shows that if we count, if for each mock, is there a departure of this given significance at least one redshift. So what you see is that over all the mocks, you virtually always going to have at least a 1 sigma divergence. Not exactly. There's a few that were completely flat, if you want. Oh, sorry. But as the limit increases, obviously you have less chances of this occurring. But you see that the interesting thing is that the multitask always have a higher chance of a larger departure, which is a good thing. This tells you that what is the most sensitive to the behavior of the data around this model, this underlying model, is the multitask. So this would mean that in the future, if you have a departure from lambda CDM, while using the multitask approach, you'll be more likely to spot this departure rather than the single task. I think it's quite important to see how robust are your results. So you want to test if what you find depends a lot or not on your, for example, on your choices of kernel or your choices of mean data. So there's no point going really into detail, but we tried all the possible stationary kernels, and what was the best actually all the time was the squared exponential. So we tested the means, the kernels, the means as well. Also something important, the range of the priors we put on the hyperparameters, because in principle, if you want to claim that your reconstruction is model agnostic, you wouldn't want, I mean, imagine you reconstruct a function and you've said C, the correlation length can be at maximum 2, and you end up finding that the best fit is 2. I mean, then you should probably put it to 3. And if it goes to 3, you're like, okay, it wants to be a big number, but I've put a prior, so it's prior dominated. So depending on how you can justify your prior, could be in conflict with this model agnosticism. When in other words, you'll have to say that your reconstruction is prior dominated. But we made, I mean, at this level of precision, that was not the case, and there was no reason to put the prior within where the hyperparameters wanted to be. Also, last thing, something I didn't see, but didn't say, but something that you could have spotted here is that the best fit, which were those dotted points here, are really very close to the mean of the posterior. So those are the marginalized one, but they're really close to the mean of their respective posterior distribution, which means that minimizing your hyperparameters will lead to something that is practically exactly the same reconstruction as if you would marginalize. So this is some Gaussian process, so I wouldn't tell you how you marginalize, you can ask me after, but that is quite important also for robustness. So a caveat, and that's why I was talking about the mean prior, the importance, and the range also on what you set on your hyperparameters, is that we applied this to current data. There's been a few papers doing that, but we didn't understand how they managed to have, let's say, a meaningful reconstruction. Because when we tried doing it, basically what happened is that, say I gave a very large possible range prior to the correlation length, then what happens is that my minimization just gives you a flat reconstruction. So this just doesn't mean anything. That means it's completely dominated by what you allow on psi. So one way to recover some sort of trend was to just limit it to a certain number. And this number here just represents the span of Z. So you actually see it quite nicely on those MCMC contours, where you see that the best fit just wants to be the maximum prior. So this typically, to me, is that GP can't currently do a robust reconstruction because the data is simply too noisy, but it will be with what we show, for example, in the future. Okay, so the last slide, salesman slide, I hope I've shown you that data-driven reconstructions are something that we have to consider in our sort of standard model testing for the future. Something to announce their power in terms of Gaussian processes is to try to compile data sets on several functions that trace the same underlying physical phenomenon. You've seen the example of cosmic acceleration, and we took growth for structures, but I'm sure there are other applications. Also wanted to promote that, well, the growth for structure are still an interesting thing to use as a test. And last part of the paper, I just wanted to show you that those mocks aren't just a fancy dream. Things are going to happen within a few decades, maybe, but they are going to happen. And here I used the forecast from SK2 Galaxy surveys, and in purple, I show the GP reconstruction. And in yellow, I don't include that data. The yellow is just the standard model predictions with the errors estimated by Planck. And so you see just an idea of how good the reconstruction will become. And we're working on a chapter 2, which is top secret. So I'm not going to say anything about, but is going to be really the following of this work that we have done. Thank you for your attention.
Thank you. Thank you very much for the interesting talk. So I guess now we take questions. Okay, I see Kavi has his hand raised. You can go ahead and ask.
Hi, Louis. Thanks for a great talk.
Thank you.
Yeah, I was just wondering, do you know why the algorithm kind of finds or kind of prefers this oscillatory structure when doing the reconstruction? Is that, I mean, you said it's a limitation of the amount of data you have, but is there a reason, like a kind of conceptual or physical reason why it would look for this oscillatory behavior? Or
yeah, you mean that the fact that it is wiggly and not flat?
Yeah.
Yeah, I mean, one reason is that well, you don't, yeah, it's the precision of the data. So your GP is just, the data is so precise that the GP is able to really trace, even if it's a tiny preference for a lower value here, a tiny one here, and a tiny one here, it just ends up that the Gaussian process is suited to detect that. So
Okay,
it's like
so
I wouldn't call that actually limitation. I would call that actually powerful thing. The other thing I wanted to tell you is that this is kind of a weird use of Gaussian processes. Here, we're not using Gaussian process in a real machine learning approach. You would use a lot of data. So here, if you imagine I added data, I multiplied by 2, then you'll start having more flat reconstruction, because you'll have let's say, a fairer balance between the amount of points above and below. Does that make sense to you?
yeah, sure. So I guess what I'm trying to ask, or maybe another way to ask this is, if in your mock data you had all the data points on the line, the means of all the data points on the line, then your simulation, your GP simulation will recover that line. Is that right?
Absolutely.
Okay. Do you have an example of that or no?
No, actually, okay. I don't. What we let me find it. We didn't put it in the paper. I have it somewhere. I'm not sure I can find it within 2 minutes.
No, it's fine. No problem. But you see that if you try it out.
Yeah, and actually we even did that. Like, let's say double the amount of actually just double the amount of data and do this average distribution for 5,000 mocks. You'll see that the precision is smaller, but also it gets flatter.
Okay.
Yeah.
All right. Thanks very much.
You're welcome.
Okay, there's a question in the chat box from Shandan, and it says, can you please give some references for genetic algorithm or machine learning techniques?
That is quite a large question. I'm not sure I'm more suited than Google to answer that. But I will point out something, though, is that today there was a Euclid paper that was released on Archive, where I don't even remember the title. You can quickly go see on Archive, where a couple of collaborators and friends who've done some generative algorithms applied to cosmology, they've released a lot in that. And I assume that it's going to, hopefully it's going to be a pedagogical description. I mean, given that's, yeah. So I think on genetic algorithm, I would suggest you to go look at this paper now and look the reference inside. Otherwise, I can also recommend Savas Nesseris. He's maybe the second author of this paper, Savas, S-A-V-V-A-S, and he has so far 2 GA papers. The first one, I think the first one is a very, not very basic, but it's like applying them to reconstructing, for example, supernovae data or something like that. So I think that could be also of interest. Other machine learning techniques, I can't give you any reference because I wouldn't know what to suggest. So yeah, that's all I can say. You didn't really ask for that, but this, what I've written down here, is the Bible of Gaussian processes, and it's free, so you can find it on the internet. You just type Gaussian process for machine learning and you can find it.
Thank you once again for the great talk, and I guess we'll see each other in the next seminar. Thank you.
Thank you very much. Have a nice weekend. Bye-bye.
Bye.